Hello, my name is Luminica Maros and I'm part of Lucas Schell's group at Science for Life Laboratory in Stockholm, Sweden. What I'm going to talk to you about in this tutorial is how you can use our new tool called GradientOptimizer to calculate an optimized gradient based on a custom retention time distribution. But first of all, before watching this video, I would strongly encourage you to read our article published in Analytical Chemistry, where you can learn more about the use of nonlinear gradients, the advantages of using such linear gradients, and the different types of gradients that you can calculate. So please read this article before proceeding watching this video. I'll just go through the basic ideas of using nonlinear gradients, and then I will explain step by step how you can calculate such a gradient if you have a certain retention time distribution of interest. As you know, most of the chromatographers are using a linear gradient for separating peptides. That means that if we would plot the percentage of organic solvent as a function of time, we will obtain a line. And this is the most typical gradient used when separating peptides. The problem with using this kind of type of gradient is that it gives an unequal distribution of the peptides over the run. This is an example of a distribution that we obtain when we use the linear gradient. On the horizontal axis we have observed retention time, on the vertical number of peptides. As you can see, much fewer peptides elute in the first part of the run compared to the second part. Following this observation, we wonder, can we come up with a different function, possibly nonlinear, such that it would provide an even distribution of the peptides across time? And this is the main idea behind nonlinear gradients, that they are functions that give an equal spread of the peptides over the run. As I said before, in this tutorial I'm going to speak about optimized gradients based on a custom retention time distribution. And the input for calculating such gradients is any retention time distribution of interest. It can be the retention times of the identified peptides, of certain peptides of interest, any retention time distribution whose spread is desired to be uniform. And that was generated with a linear gradient. What we do is we take this information and we calculate the nonlinear gradient that would even out this skew distribution that we got as input. And now I'm going to go step by step to the procedure of calculating this type of optimized gradient. First of all, you need to check that you have Java installed on your computer. And this is a MacBook, so one way to do that is just open a terminal window and type, for example, Java -version, and then this type of message will appear on the screen. So, for example, on this computer I have Java 1.7 installed. If you don't have Java installed, then an error message will appear. If you use Linux, you can check your Java installation in a similar way. In Windows, you can just Google check Java installation. It is straightforward to do that. If you don't have Java installed, you can install it from the internet. It is freely available and it is straightforward to install. Once you have Java, you have to prepare the retention time distribution that you would like to optimize. In this tutorial, I will optimize the retention time distribution of the peptides that were confidently identified in one of the runs, in our shotgun proteomics runs. So I already prepared here a file that gives the retention time of the identified peptides. So there's nothing special with this file. I'll just zoom in so you can take a look. We just have retention time 1 per line and nothing else. And this retention time can describe whatever distribution you are interested. This is the distribution that is going to be optimized. Now once you prepare this retention time, you need to download the gradient optimizer from this link that is provided here. So I'll just copy this link in a browser window. And I will reach this web page on GitHub, and I just need to press this green button where it says GradientOptimizer.jar, and I'm going to save it on the desktop. As soon as the file was downloaded, it is sufficient to just double-click it to open the main window of the Gradient Optimizer application. And this is how the main windows look like. In the upper part of the window, you can select one of three types of nonlinear gradients: in silico optimized, MS1 optimized, and custom distribution. In this tutorial, we will select the third version. Now you have two ways of giving the retention time distribution that you optimize. Either you paste the retention time in this text area here, or you can choose a file that contains this retention time, like I showed you before. Since I already have a file prepared, I will choose a file, and I will choose the file that I just showed to you a little while ago. Then next, we need to give information about the linear gradient that was used to generate these retention times. We need to give the start and the end time of the linear gradient. In this case, it is a 4 hours run between, so, and the start gradient was 10 minutes, the end 250, and it went from 2 to 40% B. Then we also have to give a parameter that is called lag time, which gives us the difference between the LC times, the times that we use to instruct the LC system, and the raw times, the times that appear in the raw file. And if you want to find out more information about how to calculate this parameter, or you don't understand exactly what it means, I encourage you once more to read our article where we describe the use of nonlinear gradients. For this data set, this value was 6.2. In the lower part of this window, we need to give information about the formatting of the nonlinear gradient. How often should we sample? Let's say we want to sample every 5 minutes, not too often. We want only 1 decimal for percentage B, and we can also add additional, we can specify additional characters that we want to have for the nonlinear gradient. Once we set all these parameters, we just press the button Calculate Gradient, and the optimized gradient will be calculated instantly. Here on the left side, you will get in a text area the nonlinear gradient given as a list of time values and corresponding percentage B, while the right side of the window gives a graphical representation of this gradient, so you immediately get an idea of how different it is from the linear gradient. If you're thinking that maybe these were not the best parameter values, maybe I should only sample at each 10 minutes, then you can modify these desired values in the main window, and then press the Calculate Gradient button once more, and then you will get an updated nonlinear gradient and an unupdated representation of this gradient. You can also, for example, add here some additional text. We want to add percentage B after the percentage B value, and then you will see that as soon as you press the Calculate Gradient button, you will see the updated nonlinear gradient here. Once you modify all this parameter value and the gradient is what you would like to have, then you can just save the gradient to a file. For example, I'm going to save it on desktop, and I'm going to call it custom gradient. And then if I go on desktop, there is a file that is called custom gradient, and if I open it, it will contain exactly this information that is present here. So there is no mystery here. And this is all. This is how you calculate the custom optimized gradient. Once more, you first select the gradient type in the upper part of the window. You give the retention time distribution of interest either by uploading a file or pasting the values in the text area. You give information about the linear gradient used to generate these retention times. You give information about the desired output, and then you just press the calculate gradient button, and that's it. Your nonlinear gradient is going to be calculated. I hope this tutorial was useful, and I'm looking forward to hear about your experience with using our software. Thank you for watching this video.